Hello. Um, in the next few videos, I'll show you how you can develop a Python model and extract weights from that model, and in future deploy it on the system you have developed on the NEORV32 plus NPU system and any other peripherals that you have added. So first you must keep in mind the limitations of the NPU. So refer to the repo for the exact list of operations supported, but remember that we do not support everything. For example, patch normalization is something we do not support. We do not support requantization for every layer, including activation. We do not support multi-channel. We do not support global pooling, for example. So these are some things that you must remember when developing your model. You must also remember the weights, the length of the word arrays your NPU supports. So the NPU on the repo, for example, for the ECP5U 5MG 85F, it supports 10 kilobytes of input, supports up to 36 kilobytes of weights. It supports 8 kilobytes of biases, and it supports again 10 kilobytes for output, whatever the output of the operation is. And this kilobytes is we use 32-bit words, which is like 4 bytes equals 1 word. Hence it's like, okay, 2500 words in the input array, 9000 words in the weights array, 2000 words in the biases array, and again 2500 words in the output array. Now, so you must remember, so of course, depending on your FPGA, you may alter these values. For example, if you have, of course, fewer BRAM blocks, you may want a max in weight tensor or weight vector, however you may interpret it, tensor B, let's say, to about 12 KB of weights at a time. So you may remember those constraints when developing your model. Another thing is how the NPU is designed right now is that all those values should be loaded together into the weight arrays. So you cannot, like, okay, after you may be creative and okay, write weights and such in time depending on the layers used, but that is not the approach we have used, at least for this demonstration. We'll just copy the weights entirely into the weight tensor at once. Now, so for this example, we'll take the 28 by 28 MNIST test. This is available on the main repo. So for 28 by 28 MNIST test, I'll go over the code briefly. So we must we have the Keras model. So we are using TensorFlow Keras. NumPy of course becomes a requirement therefore. So we import all those libraries from so for the 28 by 28 MNIST dataset, we load all the train images and train labels, test images and test labels. We add the number of channels. So MNIST 28 by 28 is grayscale, so there is only one channel. We normalize those images, so float 32 divided by 255, and train labels to categorical. This is now for this is an example model. First parameters, blah blah blah. This did not produce any good performance, so we'll focus on this. So thing about that we noticed during development is that we discovered during development was that we had to introduce fake quantization because values were getting too big, and with too big values, our accumulator, for example dense layers and convolution layers, were saturating too quickly to either ends, therefore producing wrong results. So we need to introduce this fake quantization layer using the lambda layer. This is it. So I suggest you do the same as well, especially after an activation layer like ReLU. So in the ReLU, I also suggest that you use the max value parameter 127 by 128.2. Now this you may notice that this is the exact scale of int 8q 0.7. So since the NPU only supports int 8q 0.7, we need to respect those values. You may also want to use kernel regularizers. They help you keep the values small. They don't prevent it from becoming too big or too concentrated as such. It's better that you read upon it separately. So in our case, we have 14 by 14. We have so yeah, the input shape is 14. We have 14 filters. The kernel size is 3 by 3. Now this is specifically 3 by 3 because the NPU only supports 3 by 3 kernels for now. 3 by 3 padding is valid because the NPU does not add padding on its own. So it only processes valid padding. Biases are true, of course. NPU supports biases. Then so we have the convo result. Now a strange thing to notice is the output of convolution 2D is the number of the altered dimensions after passing through the filter. So 28 by 28 becomes 26 by 26, and the number of filters becomes the number of output channels. So the actual output of the convolution layer is 26 by 26 by 14, which is 9464 bytes. You may understand that this is exactly like very close to completely filling up the output tensor, which supports 10 kilobytes even in the ECP5U5MG version. So during development, this is like the sort of discussion you need to like have with yourself and the team. Like, okay, how many filters can I support? How many neurons can I support? Etc. So you may otherwise, if you have a smaller layer, if you have a smaller output tensor, you may think about introducing an average pooling or a max pooling layer before this. So then the output of input of conv 2D would be 14 by 14 instead of 28 by 28. That's a technique we suggest. So after you're passing, so I suggest using the fake quantization layer as much as possible. There is also the need for this decorator, which we'll see later. So after you're done with so here we have 32 by 32 conv 2D. So 11 by 11 by 32 becomes 3872 bytes, which fits perfectly in our output tensor. So the input tensor and output tensor are rewritten regularly starting from the 0th index. So yeah, we pass through all these layers, and now we have a model ready. We can train that model. So model.fit. We suggest using callbacks during training, but that is up to you and how you want to handle it. You want a very high accuracy during training, like as much as possible. Reason being, this is on full 32-bit precision values, and we'll be quantizing, or will be like quantizing to Q 0.7 intake. So we'll be like losing a lot of precision, and therefore results may suffer in actual testing when you deploy your model on the NEORV32 plus NPU system. So after you are done training your model and testing accuracy, blah blah, you want to save the model as a .keras file. So in this 28 by 28 this larger model.keras was how we did it. This is the this is how you train the model. I hope you understand the weight trade-off and the fake quantization layer. The next video I'll discuss how to extract samples if you want to for testing your model on the system. Thank you.